By sheer number of engines manufactured, the pneumatic governor, perhaps better known as the air vane, was the dominant type used, finding use primarily on vertical shaft lawnmower-type engines. This application traditionally required little in the way of sensitivity or close speed control. The air vane governor system is an uncomplicated mechanism primarily consisting of an air vane, a link to the carburetor throttle shaft, a governor spring, flywheel fan, and blower housing. The air vane is free to move around a pivot point anchored to the engine. The link extends from the vane directly to the throttle shaft, where it's joined by one end of the spring. For fixed-speed applications, the other end of the spring need only go to a stationary anchor. Variable speeds require some method to increase and decrease spring tension incrementally, and the aptly named speed control bracket is typically used. Operation is fairly straightforward. As the flywheel turns, the vanes capture air and move it in the direction of flywheel rotation. The blower housing provides a pathway directing the airflow along the cooling fins to the outside. The relationship between engine speed and air movement suggests that by monitoring airspeed, we should be able to monitor engine speed as well. The air vane governor system does just so, by installing an air vane or paddle directly in the path of airflow. This air vane is tied directly to the carburetor throttle plate by the link in such a way that as airspeed and pressure increases, the vane tries harder and harder to close the throttle plate. This is one half of the governor equation. The other half is the governor spring, which is also tied to the throttle plate via the linkage. The difference is that the governor spring's job is to hold the throttle plate in the open position. Since throttle plate position controls engine speed, the governed speed of the engine, then, is the throttle plate position established when air pressure from the flywheel fins balances against spring pressure from the governor spring. On a variable speed application, moving the throttle control to the slow position reduces governor spring tension. Air pressure has a greater advantage, and the engine slows down. Moving to the fast position increases spring tension, giving the governor spring the advantage, and speed increases until the forces balance again. Now, how does the engine respond to changes in load? The throttle plate position of a lawnmower engine, running steadily at a top no-load speed, is almost closed. Only a small amount of fuel and air is needed to generate the torque necessary to overcome the internal friction of the engine and keep the mass of the blade moving. As load is applied, more torque is required. Since excess torque is converted into speed, engine speed drops because the torque is needed elsewhere to do work. Changing engine speed, of course, changes blower housing airspeed, and the governor sensing device steps in to make adjustments. Engine speed will increase if the blower housing air intake is restricted. Any restriction to the airflow into the blower housing, such as a plugged rotating screen, reduces air pressure against the vane. Engine speed will consequently rise as the governor spring has the advantage. Now, what would happen if the cooling fins were plugged, therefore closing off the exit path? Engine speed would rise. If air can't get out, it can't get in. If less air is allowed to enter, air pressure is again reduced against the air vane. The governor spring once more gains the advantage. A primary advantage of the air vane governor is that they're simple, with no complicated adjustments. They're also reliable and inexpensive. Disadvantages of air vane governors are that they're not sensitive enough for applications requiring close speed control. They are easily affected by debris buildup under blower housing and can be affected by external airflow such as wind. Adjustments are relatively simple on air vane governors. There are no static adjustments. Speed adjustments. Top no-load speed ranges are established by installing different governor springs. Fine-tuning is accomplished by increasing or decreasing spring tension. This is done by bending the stationary spring anchor in or out, or by a mechanical adjustment, such as an adjustment screw that does the same thing.